Section 4.2 is relatively short, or at least what we are going to cover of it. And it goes something like this. So a subset W of a set U is just a collection of objects that are contained in U. So for example, if U is the numbers 1 through 10 and W is 2, 4, 6, 8, then W is a subset of U, and the notation is this little, this sideways U thing, okay? So, a subset. Now, a subset W of a vector space V is called a subspace if W is itself a vector space under the addition and scalar multiplication defined on V. So think of it kind of like this. You've got this vector space V like this, and you've got this subspace W that sits inside it that never leaves, right? It stays inside itself, and it's a vector space all by itself. An example of this is like, in R3, this little plane right here, right? So as long as you add stuff that's on the floor, you're kind of still on the floor. Okay, that's kind of the idea. Now, the general structure in this vector space is the same as this one. So if this addition worked fine, then this addition is going to work fine also. And if this distributes and all of the other operations have the appropriate scalar multiplication properties, then this one's going to have them also. So of the 10 vector space axioms, only 2 of them remain, right, that aren't about the operations, and that is the closure ones. And so here is a theorem. A non-empty subset W of the vector space V is a subspace of V if and only if it satisfies the following 2 conditions. That is, the axiom number 1 and the axiom number 6. So both of the closure things. All you have to do is verify that it stays within the subset. And so here's a good example to help us get through that. So let A and B be real numbers. Show that the set V of solutions to the equation ax plus by equals 0 is a subspace of R2. Okay. Now, this actually was, if it wasn't your homework question, it was related to a homework question you had a little while ago. And so let's do this. So we're going to assume that we have x1, y1, and x2, y2 are solutions to ax plus by equals 0. And let's show what that means. Okay, so therefore, I know that a times x1 plus b times y1 is equal to 0. And I know that a times x2 plus b times y2 is equal to 0. All right? Now, the theorem says what I want to do is I want to show that when I add them, it's still in the space. Meaning, if I take x1, y1 and add it to x2, y2, then I want to know if this thing is still a solution. Okay? So, subspace of R2, I didn't say, but with the usual addition operations. So what I want to know now is this thing a solution, right? That's the question. Well, what do? You plug it in and find out. So ax1 plus x2, this is kind of fun. by1 plus y2, I know I have a weird sense of fun. So ax1 plus ax, not the subscript, ax2 plus by1 plus by2. All right. Maybe I can rearrange that. Maybe I can say ax1 plus by1 plus ax2 plus by2. Let's see. What's that? Oh, I did that earlier. That is 0. And what's the next one? That one I did earlier also. That one's also 0. So I get 0 plus 0, which is 0. So in fact, this thing is a solution. I can't leave those there. It's got cluttering up my problem, but there we go. So I know that property number 1 works, and now all I need is property number 2, and I've left myself almost no space, although I don't need much here. I need to show that k times x1, y1 is a solution. So that's going to be kx1, ky1. This should be fairly simple. So a times kx1 plus b times ky1. Okay, I can factor the k out, and I get ax1 plus by1. Okay, well, I just talked about that. It's k times 0, which is 0. Good, I fit on the page. All right. So, in fact, if you have a line, right, that goes through the origin, this is kind of cool. If you have a line that goes through the origin, then the set of points on this line form a vector space. That's really cool. All right, so anytime you take a point on this line, add it to another point on this line, you get another point on this line. All right. Fun stuff. Okay, now let's expand that a little bit bigger. Okay, so here's a theorem. The theorem says if A is a constant m by n matrix, then the solution set, solution, just one S and set. The solution set of the homogeneous linear system AX equals 0 is a subspace of Rn. Should put little vectors on these things because they're vectors here. Okay, so what the heck does that mean? Well, A is an m by n matrix, right? So this is A right here. There are m rows and n columns. And this vector x here is x1, x2, through x what? Well, this one, remember we're dotting this row with this column here? So xn, okay, equals the 0 vector. Okay. Now, this is the thing. I want to show that things that satisfy this property are a subspace of Rn. So that was my explanation for why the size is Rn. So let's say that x, let's call it, I don't know, names here. Let's pick different letters. So suppose that u and v are solutions to ax equals 0. What does that mean? That means that a times u is equal to 0 and a times v is equal to 0. All right, well, I want to show that u plus v is still a solution, right? So what is a times u plus v? Well, that's au plus av. Well, I know what those are. That's right here. That's just 0 plus 0, which is in fact 0. So directly from my definition there, okay? I also need to show that a times ku is a solution. Well, I know that constants, right? Constants can sort of go around in here. So this is k times au. Right, I know I can do that. And that's k times, I know what au is. au is 0, and then k times the 0 vector is still the 0 vector. So I'm done, right? I just showed the two things. That was a long theorem there about, well, it wasn't that long. It was a theorem about subspaces of Rn and this homogeneous system here. We're actually going to use that to our advantage later on. We're going to come back to this theorem, and we're going to need it in a later chapter here. Mostly what I wanted is to get the idea of that a subspace is a space that lives inside another space, okay? So maybe just a quick example here, since I felt like that kind of went by too quickly. If I take the 3 coordinates x, y, z, right, as R3, then the coordinates x, y, 0 is a subspace, right? Anytime you add coordinates that have 0 as their third component, they keep 0 as their third component, right? And anytime you multiply this thing by a scalar, right, it's still going to have 0 in its third component. And so these things will sort of stay on the xy plane, right? And you can do the same thing for the xz plane or the yz plane. That's kind of what I mean about a subspace. Things that stay on the floor, or maybe like this, things that stay on this plane will stay on that plane. And that doesn't work when you go off the plane, and I'll leave that to you. Okay. Now, the next section is going to be the most important one of this chapter for us, and I look forward to seeing you then.